Okay. So if I want to just wrap it up. Okay, can you see the slide?
Yes, sir.
Okay. So in slide, we came up with several ideas. So the first idea was that, this we studied when we studied ARM, and we talked about ISA-based techniques. So in instruction set architecture-based techniques, so you must have seen that in ARM architecture, you have got instruction like you have got, so let me just, so in ARM architecture, to remove branch related delays, you have got conditional execution statement, right? So you can put add with greater than or add less than. So if that condition is not met, then you would lose only one cycle. It will go as a bubble. Otherwise, it will be executed. So that was the first ISA-based technique. Second thing was for code optimization was putting S subscript after, say, algebraic instruction, so like sub S. So what this would do is that normally the plain sub instruction will not change the status of the flag. For that, you have to do subtract operation and then use compare operation to that register. And if the answer is 0, then the 0 flag will set or Z flag will set. But here, if you do this, then this would give you the result, and if the result is 0, then the 0 flag will automatically be set. So these are the two ISA-based techniques which we studied. Then forwarding and bypassing. So forwarding and bypassing, we also studied in great detail that how to get the result out of say end of execution and put it in the beginning of execution, or taking it out of memory and putting it back into the beginning of execution. Then delayed branches means you shift around your instruction so that after the branch instruction or conditional branch instruction, you've got a couple of instructions which you have to execute anyway. So that is sort of like delayed branching. Then in this particular lecture we studied dynamic scheduling, that you can remove the true data hazards. So true dependence is also known as raw hazard, as you would have known by now. Then you can do with renaming, which would remove anti-dependencies, that is war and wow hazard. Then dynamic branch predictor, which we studied in great detail. Multiple instructions per cycle, that also we studied as a part of the superscalar processor. Speculation, any branch prediction or branch prediction over several branches, and then taking instruction from different branch loops. All those things falls in speculation. Loop unrolling is something which we saw, and you're also going to do it as a part of your lab, that how to do loop unrolling. And then compiler dependent analysis. I mean, these things we have not seen, and we cannot do it right now because this compiler is not part of this course. And then finally, we just mentioned software pipelining and trace scheduling. Does anyone have any question in this particular or last lecture which we discussed? Okay, so these are the techniques which we studied. And of course, so you would have seen that some of these techniques, like up to this part, were part of any processor, be it inline processor or superscalar processor. And then, some of the instruction, some of the things were new, like multiple instructions per cycle. And then, you do speculation, with out of order execution. So these things are specifically for superscalar processor. You may get a good benefit in terms of decrease in CPI, provided you are lucky enough to get the right mix of instructions, and instructions don't have uh, control hazards amongst themselves. So that also teaches you how to write a good program. So you should not write a good program where there is too much data dependence. So people say generally that if you're trying to run your program on say inline processor or even a superscalar processor, you should not write recursion or program based on recursion methods, because that would, each result would be depend on the previous result. So you will have to go serially, and you can't go in parallel. Now the question of going in parallel does not arise till now, till this lecture. But in the next part of this lecture, we are going to study multi-core processor, where, as I discussed earlier when we studied direct cache map problem, and in this direct cache mapping techniques, when we did a problem, the last part I put two ways of writing a program. One was recursion based, which was very kind of cache friendly, but not very amenable to parallelizing. And the second was not very cache friendly, but great for doing say parallel processing. So if you have got 4 cores, then you can send him to the 4 places. Now, when I say the word that it is not very cache friendly, but does anyone want to ask a question? Someone was speaking. Okay. So if you want to do a parallel processing, as you will see now, each processor will have its own core. So some of the problems of not having a proper cache friendly program will go away, because each thread will have its own required data. So that problem will go away, and you will see how that will go away. So we are finishing the topic on superscalar processor. Does anyone have any question?
Hello, sir.
Yes.
Sir, if our loop is having only one type of instruction, then parallel processing would not be possible, right, in this loop?
Just I want to clarify. So you said that you have only one type of instruction, means all load, right?
Yes, means all load, yeah, all arithmetic, whichever.
Yeah, I got it. So then it depends on how many functional units you have. So if you have two functional units, excuse me, Vipul Kumar, can you turn off your mic, please? I'm getting a lot of feedback. Vipul Kumar, please turn off your mic. Okay, so if you have, say, two functional units, then at least two load instructions can go in parallel. So it all depends on how many functional units you have. But in general, yes, the limitation on a given particular type of instruction would be dependent upon how many functional units do you have. And even if you have two functional units, but if they are supposed dependent on each other, then also they cannot go together. Does that answer your question?
Yes, but sir, the example which you shown in class, all three functional units were supposed to do different type of task. Like a functional unit was supposed to do MAC operation, other was supposed to do load store operation. Then if I
Right.
have all matrix multiplication operations, then I won't be able to do parallel processing.
Okay. So the functional units which are shown over here, it's just for the sake of example. It is not necessarily, you may not have separate add instruction, separate multiply instruction. I would call this as 3 ALU units, and two usually multiply unit you may not want to keep separate. You may want to keep it as what do you call it? Add MAC operations. So, I mean, the names given here are not final names. These are just names given for examples, and that is to suit the kind of problem which is given over here. So, in real life, you have to see what kind of actual functional units you have, and then based on that, how your instructions will be able to go. Now, you should also remember that when people design a general purpose processor, it is not for a specific case. So, you may design a particular thing with, say, 2 load and, 3 ALU and, maybe 1 or 2 MAC. And, if you have a whole lot of MAC instruction, then, MAC instruction, some of the MAC instruction may have to use your simple ALU. So here, I want to step back and again stress a point that, your simple ALU can also do matrix multiplication. There is nothing against it, right? Your ARM7, you can write a program on matrix multiplication. It does not have a MAC pipeline, or it does not have a DSP, dedicated DSP, or does not have a dedicated GPU. So it can do matrix multiplication on its own on a given ALU. It's a very simple inline processor. The question of parallelization would come in where you have, I mean, the ideal parallelization will come in multi-core. So here, instruction level parallelism, is a very small aspect of it. The real parallelization comes, when you have got multiple cores. So just like in GPU, you have got 800 cores. So 800 different small processors. And there, what you're talking about, parallelization takes place over there. So each processor is executing same instruction, MAC. And then, data keeps on coming and, it keeps on working on it. And then, final result is compiled together and you get a nice picture or a video. Does it make sense?
Yes, sir.
Okay, so parallelization, what you're talking about, what parallelization we get in a superscalar processor is a very small amount. But, in real life, you will have 4 superscalar processor, like in 4-core machine or, quad-core chip that you might be using in your laptop or in your phone. There might be 4 such superscalar processors. And, if your operating system is smart enough, it can divide up the instructions or, your whole program into 4 parts by a process called threading. And that you will learn in system programming. So you will learn about threading and, how to make, actually, each processor can run 2 threads comfortably. So you break down your program into 8 threads. And then, you send 2 threads to each processor and, things would execute in parallel. So more of parallelization comes when you have multiple copies of a processor rather than this loop level thing. I mean, it does give you speed up, but not as much as a multi-core processor. Okay, any other question? Okay, so let me stop at this point. So now let me open another. Last time, unfortunately, I lost the slide. Okay, can you see this? Hello, can someone answer? Can you see this?
Yes, sir. Yes, sir.
Yes, sir.
Okay, good. Thanks. Now, we are going to start talking about multi-core processors. So first, let us see why we are talking about multi-core processors. Now, the whole idea of multi-core processor or using multiple processor to do one task is not very new. So in say fast computers which were used by IBM in 70s, what they used to call as mainframe computers, uh, they used to talk about something which is known as multi-processor units. So there is a difference between multiple processors and multi-core processor. So let me tell you what was happening before and now what is happening. So let me put a so previously there used to be multiple processors. And there would be like, actually it would be like, connecting a lot of computers, or at least if not computers and computer boards together. Right. So there are like, maybe it's a 4 physical computers and, you connect them together. And, when you connect them together, you can, use something called MPI. This is a type of writing program, and this is a facility which would allow you to distribute your programs into 4 computers. And that, this computer would be sending out some quantum of work to each computer, and each computer will do its part. And then, there would be maybe one master computer or master is lying over here, and all of them would be sending its completed work to it, and then work would be done. The only problem was that communication was taking up too much time. So what it means is that if there's a physical board and if there's a distance of say even 1 meter or even say 1 foot between those two processor boards, then what may happen is that when you are trying to take data from one to the other, it may take 1 or 2 or 3 nanoseconds. Now 1 or 2 or 3 nanoseconds sounds too small a time, but now as you know, some of our processors are running at 3 gigahertz. So your Intel processor on your laptop is running at between 2.8 to 3 gigahertz. So that is 0.33 nanoseconds. So one operation is done in 0.33 nanoseconds. And if a communication time is say 3 nanoseconds between different boards, and if this computer wants some data from here, then it will have to wait for many cycles. So then in early 2000, they came up with a new idea that let's have 4 cores or 4 processors on a same chip. Right? So this is your chip. So they are not separate processors, having its own infrastructure, separated by some physically measurable distance. But these are, of course, this is also physically measurable, but the distances might be in terms of microns, or even less, like 0.1 micron or something distance between these processors. So communication is pretty fast. So this they started calling multi-core processors. But this trick was used in say from 1970s only for supercomputers. So how did we do a journey from taking this idea and putting it to our laptop and desktop? So that story comes here. So this is again, tricks we have done till now is instruction level parallelism, which we studied yesterday. Then loop level parallelism we heard about. Then branch prediction, trace scheduling, use superscalar processor, VLIW, do out of order execution. So these are the tricks we explored till now, how to make your processor fast. Now, if you look back from 1990 to 2005 was an era of ILP, that is instruction level parallelism, to achieve maximum performance. So all the tricks which you use. So your first we came up with in-order processor in 1990s. You were having in-order processor, and that was giving some amount of performance. Now you want to speed it up, and you decided to, let me just blow this up, and please let me know if you still can see it. Okay, can you see it?
Yes, sir.
Okay. So, I mean, you might be too young at that time, but if you were reading newspaper in India, at least till 2008 or 2010, you'll see that Intel was producing chip after chip. So every 6 months, a new chip would come out. And when I purchased a computer in say 1995, it was DX4 100. So it was running at 100 megahertz. And it was the fastest computer available at that time. And then, 100 megahertz, the next, after a few months or it's a year or so, they came up with 200 megahertz. Then they came up with the 500 megahertz. And then they started calling this Pentium series. So Pentium 60, so 600 megahertz, Pentium 75, Pentium 90. So every 6 months or a year, Intel will come out a new chip and, would increase the frequency. So, people would say, okay, 500 megahertz processor is faster than say 200 megahertz processor. So let me go for a 500 one. Then they would say, okay, let me go for a 1 gigahertz processor rather than a 500 megahertz processor because it is supposed to be faster. But each company in its R&D department is usually 5 years ahead, thinking 5 years ahead that what kind of processors we would be making 5 years ahead. And Intel was trying to have the same experiments, with making 5 gigahertz chip and 8 gigahertz chip and 10 gigahertz chip. And they've got some very interesting results. So let us talk about that results little later. But let me just first study this graph which is given over here. So first, you are getting scalar in order processor. So, you are getting some performance. Then, you started doing pipeline and, using superscalar processor and out of order execution. And suddenly you got a huge jump in performance. So as you can see, it is more than 100% that, your performance improved. Then, you got very deep pipeline, means, instead of say 8 or 10 or 12 stages, you went into 20 stages, 25 stages. Then you went into aggressive superscalar, means, many say issue. So you use 8 issue and, use many functional units. You are using out of order, you are using speculation, all the things which is available to you. But you see, there was very little gain for the effort. Your hardware complexity was increasing. The cost of a chip was increasing. The power usage was increasing. But, performance increased only a few percentage points, 10%, 20%. So they thought that, effort is now being wasted. Along with that came other problem. And what are those problems? The first problem was known as the power wall. So they say that the progress of, say, making faster and faster processors hit a wall. In fact, it hit several walls. And wall means obstruction. It cannot go beyond it. And why it could not go beyond it? So first, take a look at this equation. This equation probably you may study later. So if you want to understand this, and if you probably don't understand what other things means, just let me tell you this, that VDD is the voltage which is given to your chip. Usually it is 1 volt or 1.1 volt in modern processors. So probably it varies between 0.8 volt to 1.1 volt. That, your alpha is the switching factor. So how many times a gate is turning on and off, and load capacitance. And this is most important. This is the frequency. So when you look at this, interesting.
Sir, here, what was alpha?
Alpha is a switching factor. So in 1 second, suppose if you are using a NAND gate. Now, as you know, the gate uses two kind of energy. The one which is shown here is the leakage power. That means whether you turn it on or off, it doesn't matter. It would leak. So just like, if you keep your set-top box on, but your TV is off, so set-top box is in a standby mode, it would still use some power. And that power would be the leakage power which leaks through the gates. Because your gates are not like perfect switches that when you turn it off, there is absolutely no connection between ground and VDD. It doesn't happen. And second one is when you switch, there is a transition power. There is a current which flows for a short amount of time. So this is the power which is used when you actually switch. And this is supposed to be larger. I mean, now this is dominating later on, but this is supposed to be larger for any given processor. So this is also dependent on switching factor. So more switching factor you have, more power will be used up. Just trying to figure out how can I. Okay, let me just bring it back to make things easier for me. So this is your frequency, and if you you can see that power usage is directly proportional to frequency. So if you go from 1 gigahertz processor to 2 gigahertz processor, the power would double. If you go to 3 gigahertz processor, power would increase 3 times. And this is one of the major terms which we have used. So if we increase frequency, the power will go up. Rest of the things, since you have not taken a course in basics of MOSFET, you may not understand. But let us not worry too much about it. Just remember this, that power is proportional to frequency. As frequency goes up, the power usage goes up. Now you'll say, okay, how much is the power usage of a chip? Well, it could be considerable for, say, Intel chip. Say, Intel chip may take up 20 watts of power, 25 watts of power, 30 watts of power. Now, you may say, okay, 30 watts of power is not that much. If I turn on a light bulb, it may take up like, old incandescent bulb, which you are using, maybe say 5 or 7 years ago in our home. It used to take 100 watts. And, it did not do any damage to itself or to the room. But the question is that, the power which is dissipated. So let's say 35 watts of power. But power alone is not the real culprit. The real culprit is power density. So power density means, okay, you are generating power of 35 watts or you are using a power of 35 watts. What is the byproduct of a power? It's heat, right? Turn on your light, incandescent bulb, 100 watts, and bulb will get very hot. So you don't want heat, you just want light, but heat is a byproduct and unnecessary byproduct, but you have to deal with it. Same thing goes for a chip. That's why your laptop gets so hot. The idea of supplying power is not to increase the temperature of a chip or your laptop, but that's a byproduct. You can't escape. So the important thing is power density. So what is power density? That you say you are generating, you are using 35 watts of power, and it will dissipate proportionate heat. But 35 watts of power, which is generated over a surface area of 1 square foot, is not much. I mean, it will cool like that. But what is the size of your chip? So size of your chip is, say, 1 micron. So 1 micron, I believe, is 10 raised to minus 6. Correct me if I'm wrong. 10 raised to minus 6 centimeter. So is it correct?
Sir,
Yes,
it is
minus 6
meter.
meters.
Yes, sir. Meter.
Okay, minus 6 meter. Okay, fine. Sorry. So if you want to find out power density, or if you just want to find out per centimeter square, 1 micron is a fairly large size. So you will get 35 multiplied by 10 raised to 6 watts per centimeter square. So what is this? This is 35 megawatts per centimeter square. Now you can imagine 35 megawatts is a huge number. And look at your size. That this in 1 centimeter square, it is almost equivalent to using 35 megawatts of power. And proportionate heat would generate. What is a normal working temperature of your processor when you are watching a movie or something? Can someone guess?
100 Celsius.
Yeah, it is around close to 100 degrees centigrade, right? So you will actually burn your finger if you touch the chip. And this is also, you're not touching the chip, you're touching the packaging. And packaging, there is a air gap in between, there is a heat shield inside. So the real thing is, and you're supposed to guarantee that your processor will work up to 140 degrees centigrade temperature. So if you are studying in the beginning, you'll say, whenever we are going to touch 140 degrees centigrade, because the room we are in sitting, even in the highest heat of Ahmedabad, maximum temperature is 45 degrees centigrade. So are we going to achieve 140 degrees centigrade? And the answer is yes. And that is because of the quantity called power density. And that was the biggest killer. So there is a talk which was given by one of the Intel's founder. And he put this graph. So he said power density in terms of watts per centimeter square. So he started saying that in 1990s, power density was around 10 watts per centimeter square because chips were larger. Then came Pentium. So you touched to 100 or whatever. But when you go higher, and he is drawn only up to here, and actually we are here. So even at this point, in the very near future, the hotness of the chip would be like sun's surface temperature of 3000 degrees centigrade or 4000 degrees centigrade. It will be that much power density of that particular chip. So that means you cannot. And the second thing was, the Moore's law was in progress. So you started putting more and more transistor in a given area. So the Moore's law said that every 1.5 years, the density of transistors, or density of gates for that matter, roughly, doubles every 1.5 years. So double the number of gates means double the power dissipation in the same area. So that means you are going to have a problem at some point. You cannot, your Moore's law has to stop. And actually it has stopped. So now if you study literature, people would say that Moore's law is no longer possible because you can't keep on increasing number of transistor in a given area for infinite amount of time. And that time has come maybe 2 years ago or 3 years ago. So the first of our thing is gone, that we cannot increase CPI by purely increasing the frequency. And because of this reason, that the temperature is increasing so much that it is burning up the chip. And your chip is burning up, so what's the point? So that's why now you don't see that, the chip, I mean, for many years, you see that, the frequency is like shuttling between 1.5 gigahertz to 2.5 or 2.8 gigahertz. And also they are making this claim that, chip is running at 2.8 gigahertz. But I did tell you that, in your laptop, I think more effect you will see in your handheld mobile, because when we studied the processor of a handheld mobile, we figured out that the chip and the handheld mobile runs at 2.8 gigahertz, but that is maximum speed. And your processor can run at that maximum speed for maybe 2 minutes, 3 minutes, 4 minutes, not more than that. Why? Because, your cell phone would start heating up. And the operating system will get a message from the sensors which are put around the chip that, okay, now this processor is heating up. So what do? How do you reduce the temperature? You reduce power consumption. How do you reduce power consumption? Reduce the frequency. So it starts putting brake on your frequency. So your 2.0 gigahertz processor would start acting like 1.4 gigahertz processor or 1 gigahertz processor when it gets heated up too much. So if you watch a movie or if you play some complicated game, your processor will not run at 2.8 gigahertz, especially in your mobile, because your mobile has no cooling mechanism other than just heat shield. And, people like us, like to put kind of a cover, which is not a very good kind of a heat dissipator. Ideally, the back of your mobile phone should be made up of aluminum so that, you can dissipate heat very nicely. But then, if you put aluminum background, then people who are holding the phone, they will burn their fingers. They would say, oh, the phone is getting too hot. I don't want to use it. Actually, the old phones, if you talk to your parents, they would tell you that the Nokia phone and others, used to get very hot. But, that was good, that, the chip would run at its prescribed speed for a long time. That heat was being dissipated. But unfortunately, it was dissipated through the back of the phone and then through your fingers. So people thought that's not a great idea. So they started putting things, which is not a very good conductor. But then, price which you have to pay is that your processor will not be able to run at the maximum speed. So we lost 1 point of increasing, one way of increasing CPI. That is by purely increasing frequency. Okay, that is gone. What is the other wall? The ILP wall, that is instruction level parallelism. So there is a limit to how many instructions you can fetch together. Like you can, as we saw in superscalar processor, that, can you bring in 2 instructions together? Can you bring in 4 instructions together? Can you bring in 6 instructions together? And, if it is not just talking, but when you say bring in 6 instructions together, you have to design data paths. You have to make decoding logic, which can decode 6 instructions in the same cycle. So that would generate heat again. So again, the power wall problem would come. And then, as I told you earlier, that, finding instruction level parallelism is slightly tough, because to execute a certain number of instructions at the same time, you have to make sure that they don't have raw hazard, and plus you have desired number of functional units. It's very difficult. So that was the second limiting unit, that ILP also was not helping you too much in lowering your CPI. What else? The third thing was the memory wall. Now, as I told you earlier, and this would make it proper, that your memory speed is not keeping the pace with the processor speed. So there is a DRAM. Now, of course, DRAM is your main memory. It is becoming slower and slower as compared to your processor. So your time, if you miss out from cache, going to the main memory time keeps on increasing in terms of cycles. Time-wise, it may remain the same, but cycle-wise, it becomes way too much. So that means there is no point of making a very fast processor, with very high number of CPI, or sorry, very low number of CPI, if you have your processor which is running, memory which is running very slow. Because even if in a 5-stage processor, we know that the fetch stage and the data memory stage have to depend on how good your memory is. And if they have, say, cache miss, either in instruction or in data, then, you have to go all the way to the processor, DRAM, and then fetch the desired result. And if the penalty is way too high, then your AMAT, that is average memory access time, would be outrageous in terms of cycles. And that means your overall CPI would go way beyond 1. It may end up in like 2, 3, 4. So that is also a factor in terms of reducing CPI. So this is the final thing. So this was the question. I remember that in 2010, people were discussing this, that the progress has stopped in making better processor. That there is problem due to power dissipation and heat generation. Instruction level parallelism is not giving us too much return, that there is only so much ILP can do. Memory is not going to be as fast as processor, because memory does take finite amount of time, and DRAM is not keeping pace with it. You can't replace all your DRAM with SRAM, because SRAM is very expensive. So your laptop, nobody would buy a laptop if it costs like 5 lakh rupees or something. So the progress of a uniprocessor, or using only one processor, was coming to an end. That okay, you have reached the limit. Now people say that this is not what is want. Science and technology should progress. And when we talk about science and technology, most of the people in this world would be very happy with having just one processor, because look at the 80% of the people who are using their phones, right? They are maybe browsing, watching some video, and most of the time watching the video is okay. There is no point of having 4K video on your phone. What's the point of having 4K video on this size? You will hardly notice any difference. It's a different thing if it's a 55-inch TV and all your things and pixelation then would start taking place. But you would not notice a difference between a simple non-HD or HD or 4K HD image, because the area is very small, so your eye would not be able to detect it. But anyway, the commercial people say you have to bring out a new product so that people would buy it. And so partly from commercial reason and partly from technical reason, because then AI and other things, that progress would have also been stopped. So that is not just commercial thing, that is a real technical thing. So that was the time when Intel people started discussing that let us bring out the old idea of using multi-processor system and make what I called you as multi-core system. And the only difference being that I will put 4 processors on a single die. That means on a single chip. So these are your 4 processors. So now it is very difficult to differentiate this. So generally people call this as a core and this as a processor. So this is, people may say this is a 4-core processor, but sometimes people change it interchangeably, because this is also a processor, and this is, if you want to be very technical about it, this is a processor, this is a processor, and what you would call it as a group of processors, right? But no one wants to call, because it's not a very catchy name, that group of processors. So they call this as a core, and this as processor. So this could be a 1 superscalar processor, 2nd superscalar processor, 3rd and 4th. So sometimes if I call this as processor, don't be too alarmed, because in literature also people jump between these 2 names, core and processor. Any question up to this point? So this is the solution which is come, and this is what we have discussed. Now, apart from this, there was also another thing which again came from old school, and that was the idea of creating threads from a program. So if you have studied operating system, I know you have not, But what does is like, if you write a program of say matrix multiplication, it is going to be one program. Now, if you know how to make good threads out of it, or you have another program which would take your program as input and thread it for you. So what it would do is it would try to find out parallelism within the program and say, okay, I can break down this program into say 2 parts or 2 threads or 4 threads or 8 threads, or if it's a matrix multiplication, I can divide it up into as many threads as there are individual matrix multiplication which are there. So that is called the idea of threading. It has been around for a long time. And here, they transported the idea of threading, which was used in a multi-processor system, into multi-core system. And, even the normal user started using the idea of threading. So if you have 8 threads, you can say, okay, even if it's a parallel task, I'll send 2 threads here, 2 threads here, 2 threads here, 2 threads here, and they will all individually calculate everything and finally combine the result and give it to me. So work can be done theoretically in 1/4 of the time than having just one processor. The only condition is that the program which you write should be quote unquote parallelizable. If you have written a program of say recursion where program is completely serial, then even if you have 4 core, only 1 core can be used. I mean, more cores cannot be used. Unfortunately, even now, quite a few programs which are written, they have like parts like, the structure could be in modern programs, structure would be a program is say serial for a part, because part of this program involves recursion. Then it becomes parallel, and then again turns into serial program. Then again becomes parallel, and then serial. So it's a combination of serial and parallel parts. So if you have 4 core machines, then what would happen if you have a serial program? Then it can use only one of the processors. Then when it becomes parallel, it would start using all 4. Then again serial, so only one processor can be used and 3 processors will have to sit idle. And then again, number of processes, number of threads can be increased because this portion of your program is parallelizable. So it can go to all 4. You will see, I mean, I'm going through this things in a little fast way because most of what I'm talking is given in the slides which is below. But I would like to tell you this, that in processors like this, what you do is your advantage is if you can thread. If you can't thread, then you'll use only one. So now you have got 4 core machines already in your processor. Now the programs which are written have been written for a long time. And there is a lot of legacy code, like your Word program has been around. And every time when they make new things, they don't start writing the program from scratch. So most of the programs you see nowadays are serial programs. So how does your 4 cores being used? So what they do like this, they use 1 core for running your Word program. I'm just giving you a hint or just an idea. Other might be using for operating system tasks. 3rd core might be used for say downloading and so on. This is known as a coarse grain multi processing. That means each task is not threaded into 4 parts, but you are giving different tasks to each processor and it is doing it. But if my problem is that I'm writing a program which should be used, it should be speeded up. So then thing is that, I have got one program and which is broken into 4 parts. And then, I get an output. So this is always possible in GPU because GPU takes only specific part of your program. And that part of the program would be this, which is usually a matrix multiplication program. And when the main processor start receiving instructions which are amenable to GPU, so your main processor will throw that instruction to GPU, and GPU would know, okay, all these instructions are coming. It knows that they're all matrix multiplication things, so it would parallelize it and start executing in a jiffy. So this is how your modern processors work. Okay, someone asked a question. What is the difference between concurrency and parallelism? Okay, so in concurrency, two threads can it work simultaneously, whereas in parallelism, you have got separate infrastructure, so you can run unrelated programs simultaneously. As I told you, you can run a Word program along with download, but you are using a coarse grain thing. Okay. Okay, so now we come down. I'm not putting too much weight, and I also don't expect you to know this too much because you are going to study this in great detail in a system programming course. So I'm not going through this. I mean, if you are interested, you can read about this. What is important is I will tell you that what I expect you to know. That I'll tell you. Other things, it's good for your knowledge, and you should understanding.
Sir,
Some people, yes,
is these threads are same as Java threads?
yes.
Okay.
Threads can be used anywhere. Now, you can use threads on a single processor also. So, what happens is, like, let's say you've got one big program, right? Like you write for ARM assembly language. Suppose if I somehow break it up, this program into 2 parts. Okay. So basically, I have created 2 threads. Now, and when I create these 2 threads, I also understand that they are sort of independent of each other, so that this execution of this does not depend on execution of this one. So suppose I've got some program and there is this load instruction over here, and this load instruction is stuck. So I say, okay, I will stop this thread and start executing the second thread. Now suppose second thread also gets stuck because of, say, structural hazard. As I said that, functional unit is not available and it is stuck at add instruction. So I'll say, okay, stop this thread and now start running this thread, because by this time your load thing would have been resolved. So that means you can start running 2 threads on a single processor. Only one thread can work at a time in a simple processor, but you can take advantage. You can hide the latency of your memory. So if something is stuck in the memory, one thread, you can say, okay, remove this process from the processor. So that means you have to do what you were doing in interrupt, means save the states on a stack and everything. And you bring in another thread, and that thread would start executing. If that thread stops for something, you say, okay, stop this thread and bring in the previous thread, because that thread now the problem would have been resolved, because now the load would have been executed. So you start bringing this thread and start working from the program counter value where you left off. Okay. So multi-threading can also work on a single processor, but its real advantage is in multiple processor or multi-core processor. Is this understood? I'm not going into too much detail of a thread, but this is all I'm telling you, that suppose if you can break your program into 2 parts, and these 2 parts are independent, it may happen that 2 parts may not be independent and one thread is depending on the result of the other. Then you say, okay, one thread has come to a point where it is dependent on the value of the other thread. Then say, okay, I'm stopping, you start. As soon as this value is available, it will tell this thread to start, and it will start again. So that is how threading works. You will be doing threading a lot in the system software course. Okay, I'm not going to do this one because this is, you can see if you want to see right now when the class ends that how threading works. But since I don't hold you responsible to do a threading. So now we are coming to the multi-core, and once again, as I told you, multi-core will have all the problems of your simple processor, of your superscalar processor, and it will have one additional program and one additional problem. And this additional problem would be cache coherency. So now you have got two types of process. I think I will have to take one more class on Monday. So I think so let me just tell you how we are going to do this. I will take one more class on 6th and then 8th. So we are going to stop on 8th. We'll keep a lecture on Thursday in your lab time. That will be a revision thing if you want, or I can do revision on 13th. I think 13th would be too late. So I'll take one extra, one lecture on 6th, and 8th lecture would be a revision lecture where, I would quickly go through things. And if you have any question, you can ask me. And on 9th, you can ask TAs if you have any question. Okay. So that is how we are going to end. Is it okay with everyone? Fine. Okay. Because I didn't want to go too fast because now there is only 15 minutes left and I don't want to rush through it. Okay. So this is now a multi-core processor, and this was the first multi-core processor. This is Intel, and you may know this chip as Core 2 Duo or Core Duo. You may have even used this in some of the older laptop or desktop. The Core 2 Duo. You can see, this is an instructive thing. This is first core and this is second core. Look at the size the L2 cache nowadays are taking. Almost the size of the cache is as big as the size of the core. That means, L2 caches are becoming too big, and that means the power dissipation is also taking a lot in L2 cache. You cannot turn a cache off. That you cannot turn power to this like sometimes you turn the power to a core or a part of a core as off because you are not using, say, video capability, or you are not using audio capability. So you want to turn that part of circuitry as off and turn it on when you start taking or listening to music or taking a picture. So this is what your L2 processor, L2 cache is. Now this is your IBM Cell processor. So Cell processor has got one power processor. So PowerPC was a very well-known thing. Now it is gone. So it had one PowerPC, and then signal processing elements were there. So these were signal processing elements mainly were for doing matrix multiplication. So if you have audio or video, it would be done by these 8 cores which are given over here. So this is a Cell broadband engine processor. So you are having one processor which is acting like a manager. This is like CPU, and these are all sort of DSPs or GPUs, so which will work under it. And it is for broadband function. So if you are communicating, then this is a cell phone processor which would work. Okay. Now we are coming to the nitty-gritty part, that we have got 2 classes of multiprocessors. One is a centralized memory multiprocessor, and we are going to talk about only this. This is what, because this is what is still in the process. This is not too much into vogue right now. So this is what we are going to study, and this is what you have in your modern laptop and desktop, and even for server. This is usually comes under distributed computing, and it is a separate area. So let us talk about centralized memory multiprocessor. So this is what it is like. So you've got this many processors, or you can call it a core. So processor 1 or core 1, core 2, and core n. So this is an n core processor. Each core will have its own cache memory. So it would have its own L1 and L2 cache, if you like. Then there is interconnect network, and then there is a common memory. So this memory, though I have shown it as a separate thing, these are not separate memories connected to each core or each processor. This is known as banked memory. So it is, that's why, there's a separate memory, but, actually in idea, this is all one memory, which is your main memory. So each processor or core has got its own cache. That means whether it's L1 or L2 or L3, whatever. Then there is interconnect network, and this is a common main memory. Whereas in distributed computing, which you may find, if you are doing computing over large distributed area like SETI project. So this is like, your laptop, this is my laptop, this is someone else's laptop. So we all have our own processor, our own cache, our own main memory. And then there is interconnect network, and, they are sharing the data. Here, as you would understand, the sharing the data, I mean, this is great, if you don't have too much data to transfer to each other. If you have too much data to transfer to each other, then, this would make it things slow. And, you have to use a different type, which you have to use for memory coherence. I will just tell you what coherence means. But, we are going to concentrate on this, that this is the picture you have to keep in mind in a centralized memory multiprocessor. So sometimes it is also known as CMM. This would also be called as symmetric multiprocessor, because the time to main memory for each one of these processors is the same, right? Because, it is one combined thing. So this is also known as symmetric multiprocessor, and it has got symmetric relationship to all processors. So all processor has got equal rights on it. So this is also known as SMP. It has got large cache, and this can scale to a few dozen processors, because finally your program initially would put hard drive, all the data would come to centralized memory. Then each processor is doing certain tasks, and they all want a block. So let me tell you what the problem is going to be here, which is specific to multi-core processor that is not encountered in, say, your inline processor or superscalar processor. So let's say, to explain it to you very simply, that it got a block X from this main memory, and this one asked for a copy of block X. This one asked for a copy of block X, and many other. Maybe let's just say these two processors asked for block of copy of X. Now that block block X will go into the cache, L2 cache, and finally it will reach to L1 cache. Now this processor does some processing on it and changes the value of a particular word in this block X. So now this particular block has changed. It is the value of this block is different from this block, and this block also is old now, because but how would this processor know that the value of this block which it is having in its cache is now suddenly outdated? Why? Because some other processor has done some work on it and changed the value of that particular block. If I don't have any mechanism, and this is known as cache coherence, that how do I update all the caches which are part of my centralized multi processor. That, I mean, this one has changed the value of a block. So how would this processor know that value of X is changed? And, if I don't have any mechanism of reconciling the differences in caches, then, this processor may go on its own merry way and, think that, I got this thing from the main memory, so value is correct. And, I will keep on working on this. So in the end, the result would be like totally weird, not something what you are expecting. So what they try to do is they talk about cache coherence. I'm not going to, because I'm going to keep the cache coherence as a part of the next lecture, but I'm trying to explain you in a very simple word and also giving you a caution. Did you hear that you should not have too many global variables in your program? Did anyone tell you that? Or do you agree with it, that you should not have too many global variables? Do you know what a global
Yes, sir.
variable is?
Yes.
Okay, so Pujan, do you know what a global variable is?
Yes, sir.
Okay, and did someone tell you that you should not use too much of it?
Yes, sir. In first sem IT course.
Okay, what is the reason for that?
Sir, because if we change the value of global variable at one point, then in whole program it will change actually. In
Okay,
everywhere where we had used it will change.
so it is coming from this phenomena. If you are using global variables, if you are using say one thread, it has only local variables, then it does not need to communicate with anything, right? And that is the kind of thing usually in matrix multiplication, that each thread is independent, it has got its own data, it knows what to do with it, and so it can work very fast. But it may not be the case in a general purpose processor. So if you have a global variable and lot of threads, they are looking at that particular global variable, and I've explained that thing in this particular problem. So I mean, this is got about a global variable thing, and you can take a look at it. But this is where the problem your global variables would create. That you will have to slow down your processor, because at some point you have to sync all the processors. And of course, as by now you would have known that there should be some message passing which should be used between processors. That's okay, I got this block from main memory, I'll change its value. If you have the same block, and if you want to use that particular block, please be aware that the block which you have is outdated, because we have very recently changed it. So now you can correlate why they were saying that don't use global variable, and from the hardware perspective. Okay, so that was the reason why you should not use too many global variables, because it would totally hamper you in improving the speed of your program. And if somehow you are not able to run program at an optimum speed, then you are going to have a problem, because cache coherence is required. So now, as by now you have figured out, the additional problem in a multi-core processor is cache coherence. So this is the topic which we'll be studying in the next class, that how cache coherence can be maintained, and this processor can work effortlessly, and even taking care of global variables which are used by several different cores within a processor system. Okay, so we'll concentrate on this. Of course, as I keep on telling you, all other problems which are faced by processors will also be faced by this. So all the problems of inline processor will be there. All the problems of a super scalar processor will be there. And in addition, we'll have to worry about cache coherence. So does anyone have any question?
Hello, sir.
Yes.
Is there an upper limit on the number of cores one can have in the centralized memory class of multi-core processors?
Yes. And I will tell you why. See, when we study the coherence and how the actual mechanism works, at that time, it will become clear to you. But right now, I can tell you very quickly. Suppose processor 1 change the value of block X. So it will have to put it on interconnect network. All other processors will be watching it. And as soon as they say, find out that, P1 announcing or broadcasting, oh, I've changed the value of X. So they all have to put a invalid flag on their own boxes. Now, all of these things are working simultaneously. So this might change the value of X. The other processor may change the value of block Y. Other may change the value of block Z or whatever. Then, there would be a lot of traffic under interconnect of just cache coherence. There would be other traffic, right? It is needing a block from memory, say I want a new block. So that also has to go through this interconnection network. So your bottleneck would be interconnection network. And that would be directly, traffic would increase if you have more cores. So that's why we say that, at most you can have 8, 10, 16 cores. Beyond it, this would be your major congestion point, which is interconnection network. And you can't have more than that. Then, you have to go to this particular thing, which is you have to use a different approach for cache coherence here. I'll just name it, but I will not discuss it. So do you see the point, Tarang, that, what is the
yes, sir.
upper limit?
Yeah, the size of the interconnection network will limit the number of cores.
Exactly. So it will be flooded with messages going back and forth. And plus, most of the traffic would be only for cache coherence. And along with it, it also has to get new blocks. It has to do write back, or, sometimes it has to do write through. So all those things, will put an upper limit on how many cores can be used for this particular thing. This is a very simple approach, and, it is very useful for our current purposes. But, so all our general purpose processor, multi-core processors are like this. Then, we have for 4 cores, it took us time to go to 8 core, but, actually we are not using 8 core. We are using 2 4-core machines or 2 quad-core processors. So it's sort of like, you can't call 2 horses as an elephant, right? 2 horses are 2 horses. It's not one elephant. So it's like that. So we are still using quad-core for a long time. And we are not moved beyond that. And one reason is the programmers. The programmers are not equipped well enough right now to write programs which can execute in parallel. So that is also one major avenue that all future programmers have to learn how to use parallel programming. Any other question? Okay, so we stop at this particular point, and we'll meet again on Monday. I will just remember, I will send you another invite on Monday, because I thought the classes are going to be over by 1st of December. That is the old timetable was work like. I didn't know that this time the classes were going to on till 12th of December. So I'll send a new invite. And please use that invite to join in. Thank you.